Sure. So is it okay if we start now?
Yeah, sure.
Okay. So today we have Wai-Kit Lam from University of Minnesota. So he will be talking about boundary and holes in first passage percolation. So Wai-Kit, you can take it away.
Yeah, thanks. So first, thank you very much for the invitation, and I'm very happy to speak here. So today we talk about boundary and holes in first passage percolation, and I don't assume that you know what first passage percolation is. So let me first define the model. So I think perhaps some of you know what last passage percolation is, and the first passage percolation is quite similar but slightly different. Okay, so the model is defined as follows. So first, consider the integer lattice ZD with nearest neighbor edges. So this script ED denotes the set of nearest neighbor edges. Okay. And then we put some weights. We call this TE on the edges, and this TE are i.i.d non-negative dependent variables. Okay. On the edges. And then for a lattice path gamma, we define the passage time of this gamma by summing all the weights along this path. Okay. And then for any 2 points, x and y, in the integer lattice, we define the first passage time from x to y by basically taking all infimum, taking the infimum over all this t gamma over all the path from x to y. So we use the symbol txy, and as I said, it is an infimum over all gamma from x to y. So infimum of this t gamma. Okay. So there's some picture below. So so basically in first passage percolation, what we want to study is this function t. So this t defines a pseudo metric on the integer lattice, and yeah, people would like to study the asymptotic behavior of this random metric. Okay. And then one way to study this pseudo metric is to study this the ball in this metric space. So we use B of t to denote a closed ball with radius t in this metric space, centered at the origin. So BT will be the set of all the points in ZD such that the passage time from 0 to x is most t. Okay. So this is like the ball with radius t in this pseudo metric. Okay. So in question that you can ask is, how does this BT look like? So these two pictures are some simulations of this BT by taking different distributions for the edge weights. So the picture on the left is I take the edge weights to be exponential random variables and look at t equals 20. Then you may be able to see some picture like this. And the one on the right is I take t to be Pareto with some parameter. And this is when t equals 6,000 and something. And the B of t looks like this. Okay. So, I mean, the pictures look, of course, different. But I mean, they share some similarities. But I think one of the main differences is that the picture on the left doesn't contain any holes, but you see the picture on the right contains some holes. Okay, so this Pareto distribution is like a heavy tail distribution. And I mean, just from these two pictures, you would imagine that the BT might look different if you consider a heavy tail distribution. So basically more holes will be present in this case. For light tail distribution like exponential distribution, you will see some region like this, and you couldn't quite see hole. Okay. So we want to understand this ball with T being large. Okay. So in fact, in a certain sense, this BT will converge to some something called the limit shape. Okay, so to make it more precise, so we will first let BT bar be like a flattened version of this BT. Okay, so BT is a set of points in the plane or in the Euclidean space. And now you add this 0, 1 to the D. In other words, you replace each vertex by a square, essentially, or by a cube. So you replace this by cubes. Then this gives you a region in RD. And then in a certain sense, this B bar converges to a limit shape. Okay, so this is, so let me call this the weak shape theorem, because there is a stronger one. I think this is proved by Kasten, and it is stated as follows. So if the probability that T being 0 is not too large, it is less than PC, where this PC is the critical threshold for Bernoulli bond percolation, then we know that almost surely, if you rescale this B bar by 1 over T, and then you look at the symmetric difference of this rescaled BT with some set B, and you look at the volume, then as T goes to infinity, the symmetric difference goes to 0. I mean, the volume of the symmetric difference goes to 0. And what is this grid B? This grid B is a non-random compact set with non-empty interior. Okay, so in other words, essentially, if you look at this BT or BT bar, doesn't matter. So if you rescale this by 1 over T, then in a certain sense, it will converge to some non-random compact set in RD. Okay. So although it is difficult to see this convergence by looking at the above picture, this is something true. But we cannot say too much about this script B. So basically we have, I mean, the only thing we know that it is convex, and it has all symmetries of ZD that fixes the origin, but we don't know too much beyond that. Okay, so we know that as T goes to infinity, this BT or BT bar converges to some limit shape, which is nice. But it is also interesting to study what this BT actually looks like. Okay. So what can we say about this BT when T is large? So we know that it converges to some limiting shape, but it is also interesting to study what does BT looks like without taking limits. Okay. So one way to understand this BT is to look at this boundary. So let me define the boundaries. Okay. So I define partial BT to be the edge boundary. So it contains all the edges x, y, just that one of the endpoints is in BT, but the other endpoint is not in BT. Okay. So in other words, it contains all the edges such that, so this edge is written as xy, where xy are two vertices, two neighbor vertices, and the passage time from 0 to x is larger than t, but the passage time from 0 to y is strictly greater than t. Okay. So I also studied another type of boundary, which is called the exterior boundary. So I'm not going to define this precisely, but just to draw a picture to tell you what it is. Okay. So the boundary might look like this. Okay, so it might connect some holes. Okay, so all these 4 components will give you the whole boundary. And for the exterior boundary, we just look at the outermost layer. So forget about the holes. We just look at the outermost layer, and this is the exterior boundary. So of course, if you want to understand what BT is, this is just equivalent to study what the boundary is. And this is something extremely difficult to study, because if you want to know what this boundary is, then you need to understand which points you can reach by time t and which point you couldn't. And I mean, if you want to know what this partial BT is, then you need to know very precisely what the passage time behaves. But this is essentially impossible. I mean, one reason is that this t, the pseudometric t, is random, so it is rather difficult to describe how this behaves precisely. Okay. I mean, because you need to know precisely what happens at time t, so I mean, just in general, it is rather difficult to describe what this boundary is. So instead, we will look at an easy question. So what is the size of this boundary?
Oh, can I ask a question?
Yes, sure.
So the holes are supposed to be negligible as time goes to infinity, right?
The volume will go to 0, yes.
Okay.
Yeah. But of course, it is after rescaling. But before rescaling, the hole can be large.
Yeah.
So I also have another question. So this set B, the one in the theorem. So it depends on only on the distribution.
Yes, depends only on the distribution. Yes.
And the other cases where this B can be described exactly?
I think, as far as I know, there's, I mean, yeah, I think essentially there's no way to describe this B precisely. For some specific distribution, we can kind of tell what this B might look like in certain direction. Like, yeah, perhaps, I mean, you can show that for a certain distribution, there's a flat edge along somewhere inside of the so-called percolation cone. But I think in general, we don't have much description what this B look like.
Thank you.
Any other questions? Yeah, by the way, I should mention in the beginning that if you have any questions, feel free to stop me, and I'll be happy to take the questions. So let's go back to our question. So what is the size of this boundary or the exterior boundary? Okay. So before I talk about how we can analyze this, so let me put a remark here is that, so as I said, perhaps some of you, or actually all of you, know what LPP is, the last passage percolation. And this problem is actually trivial in last passage percolation. I mean, at least in 2D. Because basically in last passage percolation, you can also define this BT essentially. And it is slightly different from this in first passage percolation. And I mean, basically for LPP, you can show that the boundary is always a monotone curve. I mean, at least in 2 dimensions, it is monotone curves. And so the order of this boundary must be, the order must be T. So in some sense, this problem is trivial. It's last passage percolation. And in fact, there's no hole. And yeah. So this problem only, I mean, I shouldn't say only, but it makes sense in FPP, but not in LPP. So what is the size of the boundaries? Okay, so first, from the shape theorem, so we know that this BT, after you rescale by T, it converges to some non-random convex set in i.i.d. So we know that the number of points in BT, or the volume of BT bar, must be of order t to the d power. And because of this, then you can immediately conclude that the edge boundary, actually either exterior boundary or the whole boundary, it must be upper bounded by t to the d power and lower bounded by t to the d minus 1. Okay. So the left inequality flows from the isoparametric inequality, and the right one is kind of like a trivial bound. Okay. So of course, these two bounds don't match with each other. So can we say something sharper? Okay. So in fact, there is a final version of the shape theorem, which was proved by Alexander in 1997. So if you assume that again, there are not too many zero edges, and you also assume that the TE has an exponential moment, then you can show that almost surely the BT or BT bar is contained in an annulus, essentially. So after you rescale this B by some factors, t plus minus some constant times t to 1/2 times log of t, then this BT bar will contain in this annulus for large t. So basically the picture is as follows. Okay. So these are the two, so this outer layer is t plus t 1/2 log t times b, and the one inside is the -1, and the bt will lie in somewhere here. So this is bt bar. Okay. So this happens for large t. Okay. So there are some refinements of this results. So I think there's some improvements. So you can essentially replace this log of t by square root of log of t, and you can also reduce this moment assumption. But I mean, in any case, the picture is not that different from this one. So if you believe this result, then you can conclude that, I mean, the edge boundary will be upper bounded by the total number of edges in this annulus. So you can conclude that the edge boundary, in this case, will be bounded about by some constant times t to the d minus half times log of t for large t, almost surely. Okay. But of course, this upper bound is still not good enough, because we know that the lower bound is t to the d minus 1, and the upper bound, now you have t to the d minus 1/2. And I mean, these two bounds are quite different apart from each other. So, I mean, the reason why we got this upper bound here is because we just count the total number of edges in this annulus. But I mean, this is of course a very crude bound. And I mean, just you can see from the picture above, the simulation pictures, the boundary, although it is a little bit rough in some sense, but I mean, you can see that this student occupied all the edges in that annulus, because I mean, if you assume that the edge boundary kind of take all the edges in this annulus, then this boundary is like a space filling curve, and this is something that we would not expect. Okay. So in a certain sense, this bound is not good enough. Okay. So can we get some sharp bounds for the boundary? So this is the question that I want to address. So from now on, we will always assume that the probability that TE being 0 is less than PC. Okay. So always assume that there are not too many zero edges. Okay. So it turns out that we are able to give some bounds depending on another random variable. We call this Y. This is the minimum of too many edge weights, where it is T1 and so on. These are i.i.d copies of T. So in joint work with Michael Damron and Jack Hanson, it was like 3 years ago, we showed the following. So first, let me tell you what we can get for the upper bound. We can show that there exists a constant C1 such that almost surely so if we look at the set of our S in 0T, such that we look at the size of the edge boundary at time S. Okay, so you look at the set of this edge boundary is larger than some constant A times S to the D minus 1 times the expectation of minimum YS. Okay, so I'll explain this term later. So we look at the set, and then we look at the measure of the set, and then divide this by T. Okay, so this is like the density of time such that the boundary is large in the sense that it is larger than the thing on the right-hand side of this inequality. So we show that at T goes to infinity, this is bounded about by some constant over A. Okay. So I'll explain what's going on later. So there's another inequality that we can prove is that we look at something similar, but instead of the whole boundary, we look at the exterior boundary. Oops. Exterior boundary. Okay. So we look at the set of all times such that is large. Large in the sense that it is larger than some constant times S to the D minus 1. And now you look at the back measure of this again, divide this by T, and then take T to infinity. Again, this is multiplied by some constant over A. Okay. So what does this mean here? So meaning. So take A large. So when A is large, then the right-hand side is small, of course. And so the left-hand side is also small. So in other words, the density of time such that this inequality holds will be small. Okay. So in other words, for most of the time, this inequalities inside this set wouldn't hold. That is, for most time, the reverse inequality will hold, which means this, the boundary has size no larger than some constant times T to the D minus 1 times something that looks real, expectation of whatever. Okay. And for the exterior boundary, we know that for most time, the inequality inside the set wouldn't hold, so it is bounded about by some constant times T to the D minus 1. Okay. So this is the meaning of this statement here. So I'll explain what this expectation means in a moment, but before that, let me talk about the lower bound. So we can show that there exists another constant, say C2, such that almost surely if you look at the edge boundary, we can show that the size is always bounded below by some constant C2 times, let me see, max of t times the probability that y larger than t, and 1 times t to the d minus 1 for large t. So the lower bound is essentially t to the d minus 1 times some factor. So this holds for all large t. Okay? So the difference for the upper bound and lower bound is the upper bound we can show that this holds for most times, but not for all time. And the lower bound would hold for large t. So let me give a brief summary for the bounds. So first, we know that the edge boundary is upper bound by t to d minus 1 times this expectation. This S should be t. And lower bound will be again something times t to d minus 1. Because now you have a max of 2 terms. While for the exterior boundary, we know that for most time it is boundable by t to d minus 1. And we also know that by isoperimetric inequality, the lower bound is t to the d minus 1. Okay. So again, let me emphasize that this bound on the rates just hold for most times. Okay. So let's look at some examples to see how we can understand the upper bound and lower bound for the boundary, because it might be difficult to understand this expectation, and this t times the probability that's y greater than t. So first, if the mean of y is finite, then you can show that for the right-hand side, the expectation here, as t goes to infinity, by say the dominated convergence theorem, it converges to the expectation of y. Okay. So in other words, the upper bound is t to the d minus 1. And for the lower bound here, when this mean is finite, by Markov, the probability is bounded about by this mean divided by t. And so this term here is bounded about by the mean. Okay. So the max here will be just a constant again. So the lower bound is also t to the d minus 1. However, the bounds can be larger if the distribution of y has some tail that looks like 1 over t to the 1 minus alpha, where this alpha is some number strictly between 0 and 1. Then let me skip the calculations here. You can show that both bounds will be t to the d minus 1 plus alpha. So in other words, basically, I mean, just look at this second inequality here. You know that the exterior boundary is basically more or less smooth in some sense because it is of the surface order. But for the boundary, the whole boundary, you see that the boundary can be larger if you assume that this y has some heavy tail. But I mean, as long as the expectation of y is finite, then again, the boundary is also more or less smooth in some sense. Okay. But when the tail behavior of y getting worse and worse, the boundary can be larger. But still, no matter what happens, the exterior boundary is of order t to the d minus 1. So basically, there's only one reason that this can happen, is that there are many holes in the boundary when you have a heavy tail distribution. So there are lots of holes. So actually, this can also be seen from the simulation pictures I showed in the beginning. For exponential distribution, you couldn't see many holes. Basically, I mean, just look at this picture, you couldn't see holes. And I think there should be some holes, but because the picture is too small, so you couldn't see any holes. But for heavy tail distribution like the Pareto, you see that there are some holes present. So of course, the natural question will be, how can you describe the holes and what do we expect? Okay. But let me see. Yeah, but before that, actually, these two are not the only things that we proved. Okay. So because the upper bound holds only for most times, it is not very satisfactory in some sense. So are we able to prove something stronger if we assume something more? Can you show the upper bound holds for all times instead of most times? So in fact, we are able to say something, again, in the same paper. So if you assume that the limit shape is uniform curved, so I'm not going to define what this is precisely. So if I assume that this is uniform curved, but I have to mention that this assumption here is unproven, although it is believed to be true for, say, if T is continuously distributed, this should be true, but it is not known whether there's a distribution that indeed gives you a uniform curved limit shape. And if you assume that T has an exponential moments, then we can show that the edge boundary is bounded above by some constant times T to the D minus 1 times some polylog vector for large T. Okay. So if you know some information about the limit shape, which unfortunately we don't actually have this information, then we can show that the boundary is bounded above by essentially T to the D minus 1. I mean, of course, you cannot neglect this polylog vector, but essentially this tells you that the order should be T to the D minus 1. But again, this is assuming the limit shape it has uniform curvature, and this is something that we don't show whether it is true or not. Although, again, as I said, we believe that this should be true for a large class of distributions, at least. So, yeah. So again, the reason why the boundary can be larger than the exterior boundary is because essentially there are lots of holes in this BT, this ball here. Okay. And in fact, the way we find the lower bound for this edge boundary is just to create a lot of holes. Okay. So because of time, I think I'm not going to describe how we prove this, but yeah, just want to mention that in the proof of the lower bound, the idea is to construct a lot of holes, which is of size 1. Okay. And we show that there are actually a lot of this kind of holes so that you can get a larger boundary when you have a heavy tail distribution. Okay. So again, the holes we created when we prove the lower bound is to create a hole, a lot of holes which are of size 1. Okay. So a natural question is, other than this little holes of size 1, can we, do we expect some holes that are larger? And what is the size of this holes in, typically? Or another question that you can ask is that what is the size of largest hole? And for this reason, we consider the following: m of t is the size of the largest hole as time t. Okay. And it is perhaps not very difficult to show that. In fact, you can show that the lim sub of this m of t as t goes to infinity will be infinite. Okay. So in other words, when t is getting large, I mean, you expect that there is a sequence of times, an infinite sequence of times, so that at time t it has a very large hole. So this is true as long as the distribution is not trivial. In other words, the support of the law of the edge weights is greater than 1. So as long as it's not trivial, then you can show that this m of t, the lim sub of this m of t is infinite. Okay. I mean, this might be difficult to show for general distributions, but you expect that you should be able to create a particular distribution which has, say, infinite support. And I mean, you should be able to show that this is true. It's not that difficult. But can we say something more? So in an ongoing project with Michael Damron, Julian Gold, me, and Xiao Shen, so it's ongoing. So we are able to say something more about this m of t, the size of the largest hole. Okay. Suppose that the distribution is non-trivial. I mean, basically, if the distribution is trivial, there's no way for you to create a hole. But as long as it's non-trivial, then the following holds. First, almost surely, the lim inf of this MT is also infinite. So in other words, for all large time, you will expect to see a very large hole. This is, I mean, kind of out of our, I mean, if you just look at the simulations, it's kind of surprising because, again, go back to here. Although I mean, for the picture on the left, you couldn't see any holes, but actually, when t is getting larger, you will be able to see a large hole. Of course, I mean, you couldn't see here is because one reason is that this t here is really small, so you couldn't see any hole. Okay. But it turns out that as long as your distribution is something non-trivial, there is always a large hole when t is large. And moreover, you can also show that the number of holes as time t is of order at least t to the d minus 1 for large t. Okay. So not only there's a large hole for large t, and you can also show that the number of holes is at least surface order. And in fact, if we further assume that the edge weights are uniformly bounded by some number, say b, this b is some finite number, we can also show that this m of t is at least log of t. Yeah. So if you assume that the distribution is bounded, we can even give a lower bound for the size of the largest hole. Okay. So this is the lower bound for the size of the largest hole. Okay. And we can, I mean, to show upper bound, it is, I would say, much more difficult. But if we assume that, again, B has uniform curvature, then we can say something. Again, I have to emphasize that this uniform curvature is not proved. But again, it is widely believed to be true. And we assume some exponential moments. And we assume we're in 2 dimensions. Then we're able to give an upper bound for the size of the largest hole. There exists 2 constants, C1 and C2, such that this m of t is bounded above by some C1 times log of t to the power C2. So again, this is for large t. So basically, I mean here, if you believe that the limit shape is uniformly curved, then, and if you further assume that the edge weights are uniformly bounded by some non-random constant, then you see that the size of the largest hole is somewhere between log of t and log of t to some power. Of course, it would be good if this C2 can be taken as 1, but we couldn't quite show this. I mean, up to this point. So, yeah, so this is what we can show. Okay, so let me give you a brief idea how this can be proved. So for part A, we will just focus on the case that T is bounded. And that's conditional on this ball equals some set B. Okay, so we know that this BT looks like this. So this is B. And now you look at an edge on the boundary. Okay, so if it is on the boundary, actually the situation is quite complicated. So if you know that this edge is on the boundary, there are not too many things that you can say. And in fact, the law or the distribution of this TE will be different from the original one. But the idea is, well, I mean, I think I should mention the idea first before talking about this edge here. I mean, the idea is to try to create a local configuration here so that there's something looks like this. So let me draw a picture like this. So you can create some local configuration like this. And the one in green, I mean, this is some path or some circuits here. And all this green lines here are of low weights. Okay, so all the edge on this green path here are of low weights. And if you assume that all the things outside of this green region here, I mean, all the things here are of large weights, then you can imagine that, well, first, I mean, this B here is BT, and then you take an edge, E here, and then you enter this region. And because all these green edges here are of low weights, they will be kind of inflated first. And then after some time, you will be able to create a hole with a suitable size. So this is the idea. Okay. But the difficulty here is that this E here, I mean, the distribution of E of this TE here is something that we don't actually know. Okay. But if you assume that the edge weights are bounded, no matter what this distribution is, you know that after time, I mean, after a B time units, then this E will be inflated. In other words, this E must be in the ball with radius T plus B, because we assume that all the weights are bounded. Okay, so we know that at time T plus B, this edge will be inside of the ball at time T plus B. Okay, so in other words, you know that what's going on after you invaded this E. Okay, so you will go along this green line here essentially, and then wrap around, and then you create a hole. So basically, if there exists just a local configuration, then you know that there exists a hole with a known size at a known time. And if you further assume that the radius or the side length here of this cube or this box here is log t to some power, say 1/d. Okay. So if you condition on b of t equals b, then everything outside this region b will be independent. So if you want this local configuration to happen, I mean, if the siphoning of this box is log t to the 1/d, then the total number of edges in this box is of order log of t. And therefore, with probability at least some number epsilon to the power log t, you will see some local configuration like this. And for this, I mean, the boundary of this B has order t to the d minus 1 many edges. So essentially, in some sense, they're like t to the d minus 1 many independent trials for you to create this local configuration. And so this is how we can show that when t is large, there is always a hole with a appropriate size. So this is the idea. Okay. And you see that we indeed need the fact that this t is bounded to have this argument, because if t is not bounded, then if you look at the edge here, which is on the boundary, you cannot say that this will be inverted after a certain time. Okay. Of course, it will be inverted after a random amount of time. But the point is, there's no control how you can make sure that this edge is invaded after a fixed amount of time. So you need some more technical arguments to show that indeed this E will be inverted at some point. Okay. But I'm not going to talk about that here. So this is the rough idea how we can show the largest hole is of size at least log of t. So let me perhaps also say a few words on how you can show that if the limit shape is uniformly curved, then you can get the upper bound for the largest hole in 2 dimensions. Okay. So why would curvature helps? It is because if you assume that the limit shape is uniformly curved, then you can, in some sense, you can control the geodesic. The geodesic means the time minimizing path. So we can control geodesic wandering. So what does this mean? So basically, the idea is, so we first fix a y, which is a pointer. Okay. And then you look at you assume this y is belong to some geodesic from the origin to some other point, say x. Okay, so let me draw a picture. So this is the origin, and y is here, and perhaps it then lies on some geodesic that's ends at x. Okay, so assume that y is on such a geodesic. Then if you assume the limit shape is uniform curved, then you can show the following. So essentially you put a cone, or let me just draw a rectangle here, around this vertex y. And the width here is like of all the log of y. And the height here is, roughly speaking, y to 1 minus epsilon. Okay. So you can show that, I mean, if you look at this boundaries here, so this three sides boundaries here, you can show that with probability at least 1 minus e to some constant times the log of y to the delta power for some delta positive that you fixed in the beginning. Then you can show that with this probability, the geodesic or the line segment yx, by line segment I mean the geodesic segment. Okay, so you look at the segment from y to x, the blue line segment here. This will not touch these three boundaries. Okay, so in other words, if you assume that the limit shape is uniform curved, then essentially the geodesic wouldn't wander around. It will kind of flat in some sense. Okay. And because of this, I mean, if you believe this picture, then if you look at a situation that there is a large hole near the boundary, okay, so say this radius here is like log of t to some power. Then if you look at the point here, say z, then if there's a hole here, and if you want to reach from 0 to z, then no matter which path you take, it must be the case that you have to kind of travel in this way. So you must be kind of get rid of the hole, because this is, this is something that you cannot reach. Okay, so you need to kind of get a detour like this. However, if you need to go in this way, then because of this picture above, then this geodesic will kind of wander around, and this will kind of violate this picture above. And so this couldn't happen with high probability. And the reason why this argument only works in 2 dimensions is because, well, in 2 dimensions, you can rule out that the hole cannot have width like this. But in 3 dimensions, you can still rule out the case that if the hole is of 3 dimensions, whatever it means, then this picture couldn't happen. But you cannot rule out the case that the holes may look like a 2-dimensional holes, or even something smaller. So you cannot say that the size of the largest hole is bound about by something like log t to some power. Okay. Yeah. So this, we are still trying to improve the lower bounds and upper bounds in this case, and hopefully perhaps we'll be able to write down something later. So this is what I want to say. Thank you.
Thanks, Wai-Kit, for the talk. So let me stop the recording.